So here comes the final major video in my spatial econometric series. In the last video, down here, spatial regression in R1, we looked at the four simplest models: ordinary least squares, the spatial error model, the spatial lag model, and the spatially lagged X model. And in this video, we're going to look at all the other flavors of models, or at least the main flavors of spatial econometric models, and we're going to talk about how to think about specifying the right model and how to do some specification tests. After we get done with this video, if you've watched all the others in this series, you should be able to say that you have a good, basic, solid understanding of an introductory view of spatial econometrics. So congratulations. There's a whole lot more to do though. So please let me know if you want to learn more. I will keep going. I can teach you some more about this stuff. I can do some interviews with some of the top people who are researchers in this field and have them explain some things and ask some questions if you like. But I'm only going to do it if you let me know that this is what you want me to do. Thank you so much for your support so far. I really do appreciate it. So let's dive into this video. So you're going to want to download the zip file, and in that zip file I'm going to have a couple of PDFs. I'm going to have an updated version of my spatial regression cheat sheet. I'm going to have a file that we're going to look at today that shows all of the common kinds of models and shows you what nesting of models means when we test these restrictions. I also have a map file we're working with that has some spatial data, the same one that we worked with in the previous video, and I have a commands list here, a text file that we're going to use. So download that zip file, unzip it into a folder, create a new RStudio project. I showed you how to do that in the previous video. And now we're going to go File, New File, RScript. And we create this new project in the same folder that has the map files and everything else in here. And then what we're going to do is we're going to copy the commands from our SPReg video 2 commands into this little RScript window. So we open up this in our favorite text editor, which for me is Notepad++. Copy those and paste them here. For your convenience, at the end here, I put the commands from video 1 in case you want those in the same place. But what we're going to do here at the top is we are going to make sure that if you're on a different computer or if you're just starting this, you have everything that you need. So if you need to install these packages, spdep, rgdal, and rgeos, go ahead and run those commands, highlight them, click Run up here. And in this block of commands, we are just creating some of the objects, the weights matrix, some of the basic regressions we did last time. So again, you can run these individually, or you can highlight them and hit Control Enter, or click the Run button up here. And now we see over here on the right that we have these four simplest regressions. We also have the Queen weights matrix that we created last time. So assuming that we've already looked at our OLS, our SLX, our lag Y, and our spatial error, and if you're interested in investigating your model specification using the Anselin method, then you can look at those Lagrange multiplier tests. Today I'm going to talk about the more modern approach to spatial specification. So let's open up our PDF that has the nested models on it. So here I have up at the top the Manski model, which is the most complete kitchen sink, throw everything in there kind of model that has the lagged X's, the lagged Y's, and the lagged, spatially lagged error terms, and showing you how you can simplify that Manski model, which most people I talk to don't think that's a good idea to run the Manski model. but how you could simplify the Manski model into either the Collegian-Pruka, also called the SARAR, SAC, or the Clifford model by making the spatially lagged x's, those coefficients all 0. That simplifies down into the Collegian-Pruka model. Then you can simplify that down into the spatial error or the spatial lag or OLS by simplifying. So the Manski model and all the models in this left column here are nested, which means you can get to one of the simpler models from one of the more complicated models. Similarly, here, the center column, these are all nested models. So if you started with the Manski or the Spatial Durbin model, the Spatial Durbin has lagged y's and lagged x's, then you can simplify that Spatial Durbin model into an SLX, a spatially lagged y, or the spatial error model, or OLS. And similarly, if you start with a Spatial Durbin Error model, the Durbin Error model does not have the lagged y, so if you start with a Spatial Durbin Error model, you can simplify that into either the spatial error or the spatially lagged x or OLS. So the Spatial Durbin Error model does not have lagged y's. So if you go with a more modern version of a spatial specification search, then what Jim Lesage would say is, look, don't worry with the Manski model. And he makes some arguments against the Collegian-Pruka model. So let's ignore the left column over here. And he says that you should really start either with the Spatial Durbin model or the Spatial Durbin Error model. And which of these two you use is going to depend on whether you think your data generating process, whether you think the relationships in your model are local, in which case use a Spatial Durbin Error model, or are they global, in which case use a Spatial Durbin model. The big difference here is the global model has the lagged y. And by global, what we mean is that if something happens in one region, a global model is going to have that impact from one region spill over to every region in your data set. So that's a global model. So if something happens in one region, that spatially lagged y is going to allow that change to propagate or have an impact on every other region in the model, even if they are not specified as neighbors. The Durbin Error model, on the other hand, is what we call a local model. In this model, if something changes in one region, it is only going to impact the direct neighbors of that region. So a few sources you should probably read if you're interested in the idea of spatial specification are Elhorst's 2014 book, Lesage and Pace's 2009 book, and Lesage's 2014 paper. Start with Lesage's 2014 paper. I have the sources down here at the bottom. The paper is open source. It's at the Review of Regional Studies, where I used to be an editor. And it's an open source journal, so it won't cost you anything to download and read it. And it's a nice brief treatment of why he thinks the Spatial Durbin model or the Spatial Durbin Error model are the best two starting places. And again, think about where you should start. Do you need a global specification? If so, include the Durbin model that has the lag y's. If it makes more sense that only neighbors are going to be affecting their neighbors, and there's not going to be this ripple that continues through the entire space, then choose the Spatial Durbin Error model as your starting place. And then we're going to use likelihood ratio tests, and we'll do that in just a minute. All right, so let's go into R here. So we've just run and stored our 4 simplest models, and we'll have those for later, and we'll look at those later. But if you wanted to follow, again, the more modern approach, decide whether you want the Durbin Error or the Durbin model. Now, just so you know, and this is on my Spatial Econometrics cheat sheet, let's run all these more complicated models that are on our sheet. So the Spatial Durbin Error model, here's our command, error SARLM, type equals E mixed. So that'll run the Spatial Durbin Error model. Let's just run these and add them to our list of saved objects over here. Reg 5, Spatial Durbin Model is type equals mixed. Command is lagsarlm. Again, these are all in your text file and on my spatial regression cheat sheet. The Manski model, if we wanted to do the kitchen sink model with everything thrown in, is sacsarlm, type equals sac mixed. And the collegian Pruka model, if we wanted to have a look at that, sacsarlm, type equals sac. Okay, so now we've got all of those models run. Now, just because somebody's going to ask, remember when you run the Lagrange multiplier tests using the Anselin method, one of his tests is for a model called a SARMA. As far as I've been able to tell, I haven't been able to find a command in R that will run a SARMA model. But remember that even Luke Anselin said that in his opinion, the SARMA is probably never going to be the right model to begin with. That he just included the test for SARMA for completeness, as he called it. Okay, now let's have a look at these results very quickly for each of these models just to see what we expect to see in the output to help us tell what we're looking at. So we could type summary and then the name of the regression we saved it to, but just to save some typing, I'm lazy. So I usually do this command s equals summary, or I should more appropriately do assign the word summary to s. I'm trying to get into a better habit instead of using equals, using the assignment operator. 99.9% of the time it's the same thing. What this does is allow us, instead of typing summary every time, we can just type s as a shortcut. So let's look at the results for these just to see what we should be seeing. So OLS, we shouldn't have any spatial things going on. Here we just see our normal coefficient estimates. With the SLX, we should have two sets of slopes, one for the own effect and one for the neighbor effect of that variable on our region. For the lag y, we should be seeing a rho, which is the spatially lagged y multiplier. And so here we see rho as 0.398. With the error, we should be seeing the multiplier lambda down here, 0.40, for the error multiplier. So that roughly says that when the average of our neighbor's residuals are higher by 1 unit, then our residual will be higher by approximately 0.40. Spatial Durbin Error model builds in the errors and the lagged x's. So here we see the two sets of coefficients here. And again, what we're explaining here as our dependent variable is the DUI arrests, the driving under the influence rate of driving drunk, basically, for each county. Let's go ahead and run the rest of these, and then let's think about which of these models do we think might be the one we should start with, instead of just running all of these. We're running all of these just for fun. So we just ran the Durbin error model. Here's the Durbin model, the global model. So here we have the lagged x's, and we have rho, which tells us the impact of the neighboring y values. And then the Manski model, Reg 7. So here we have the lagged x's, here we have rho, and we have a lambda. So we have the lagged y's and the lagged error term thrown in there. And then the SARAR, or SAC, or collegian Pruka model, is the one that has the rho, which tells us the lag y, and the lambda, the lagged error, but it does not have the spatially lagged x values in there. So with all these models, how can we tell which one's best? Well, when it comes to specification, as I said, the best thing to do is to try to think about which model is best. You need to understand these models and what they're trying to do, and use a model-driven approach. Use what you know about the data. Since what we're trying to explain here is, again, let's go back up and look at our model, how many people are driving drunk in a given county, and we're trying to explain that with how much liquor is sold per capita, What percentage of people in the county are enrolled in college? So do college students drive drunk more? What's the distance between where people can buy hard liquor and where their homes are on average? What percentage of people in that county are Baptists, because Baptists are historically against drinking in the United States? What's the average distance between people's homes and the nearest place where they can buy a mixed drink like vodka and orange juice in a restaurant? And what percentage of people in this region work in the entertainment and recreation industry, trying to control for tourism? What we should think is this a global model or a local model? Is there any reason to think that if something happens in one county, that effect should spill over to the entire state? That's a global model. So do we think the impact of driving drunk is going to be something that where if one county, more people are driving drunk, or if more people are in college in one county, should that affect the driving drunk arrests in the entire state, this ripple effect? Or should it be a more local effect where, well, maybe if more people drive drunk in one county, that could have an effect on people driving drunk in the neighboring county. But just that neighboring county. It's probably not going to spill over to 2 counties away or 10 counties away. I think it makes sense to me that we should look at this as being a more local process. I certainly think that people do drive from one county to another very frequently, and you might go to a bar in one county and then drive back home to your home county. So I think a more local model might make more sense. So what Lesage would suggest is start with a Spatial Durbin Error model. Estimate that, and then see if we do a likelihood ratio test. Does the likelihood ratio test suggest we should restrict that Durbin error model back to either a spatial error model or an SLX model or OLS, a non-spatial model? So let's do that and see what happens. So let's look at the results for that Spatial Durbin model one more time. So again, the Spatial Durbin model, we have the impacts of the coefficients on our own county. So if there are, say, more college students in our own county, positive coefficient, but not statistically significant. So we probably also want to look at the impacts, and what this is going to do is just give us a summary of those direct and indirect effects. How do variables affect my own value of the dependent variable, and how do neighbors affect my value? So let's run this impacts command. Now this version of the impacts command is not all that interesting. It just gives us the direct, the indirect, and the total, which really we can get from up here. Sales per capita 0.1657, the indirect sales per capita 0.038, and the total in this case is not the sum of these two effects, the direct and the indirect, as they would be in just an SLX model. Because of that lagged error structure, the total is going to be a little different. Now, what we really want to know is what are the p-values. So we want to run this next command that will give us zstats equals true. And here we can get a list of the z-stats and the p-values for the direct, indirect, and the total effects. And this is more informative than just looking at this output right here. Okay? So when you're doing a project, you do want to report this original table here that is given to you by R, but you don't want to use this table for inference. What you want to do when you spend your time interpreting which values are statistically significant, you want to use this impacts table with the p-values. So you want to focus on some of these variables will have a statistically significant direct or indirect effect, like percent of people working in the entertainment and recreation industry. 0.04, indirect effect is statistically significant. So a county might be concerned if they are next to a county that has a large entertainment industry. However, the total effect we can't be so sure of. So this means if in the entire state we had more of an entertainment industry, we're not as sure because this p-value is 0.074. We can't be as sure saying that there is an effect there of raising entertainment spending or entertainment employment in the entire state. We're just a little more sure with this p-value of 0.04 that there's an effect if our neighbors have a large entertainment industry. So you have to be careful when you're interpreting this. So lambda is the multiplier on the residuals. So if there's a higher unexplained value for drunk driving in a neighboring county, that increases our residual in our county for drunk driving arrests. And that p-value is extremely low. Okay, so what should we do now? Well, if we're not sure if this is the right model, we might say, well, not a lot of those lagged x's are statistically significant. Maybe we should think about restricting this model to a simpler model. So we started with the Durbin error. 3 things we could possibly simplify this down to would be to drop the lagged x's and just make it a spatial error model, drop the lagged errors and just make it an SLX model, or maybe just OLS. Maybe we don't need spatial effects. We could just go with a regular ordinary least squares regression. So let's test those restrictions and see what happens. So here are our likelihood ratio tests. So the null hypothesis we're testing is that the restrictions are true. In other words, the null hypothesis, we should restrict the model to something simpler. So if the p-value is low, we reject the null hypothesis and we are not going to restrict the model. So here's our command, lr.sarlm, and then you put the 2 regressions. So you have to run the regressions first, and then that gives the likelihood values, and then you use those in a likelihood ratio test. So lr.sarlm, this is the SDEM, Spatial Durbin Error Model. Let's see if we should restrict that to the spatial error model. So the test here says that the likelihood ratio is 19, 6 degrees of freedom. The degrees of freedom are how many things we're restricting. And what we're restricting here are these 6 lagged coefficients to be equal to 0. So that's why the degrees of freedom is 6 there. And it says our p-value is 0.004. So we should probably reject the null hypothesis that we should restrict, and we shouldn't restrict this model to a spatial error model. All right, well, let's see, should we, and this is just telling you that the order you put these arguments in is not important. So you'd get the same thing if you put reg 4, reg 5 as reg 5, reg 4. What if we tested to see, should we go to an SLX and drop that spatial error structure? Here the degrees of freedom is 1 because we're only restricting one parameter, that lambda, to be equal to 0. And the p-value is very, very small. So we probably shouldn't restrict this to be an SLX model. So this is saying that if we're pretty convinced that we have a local structure, not a global model, but a local model should be used, that the Spatial Durbin Error model is probably the right one. We shouldn't restrict it. Now, if we wanted to, we could go ahead and see, well, should we restrict this back to an OLS? I can already tell you that we shouldn't, because if we shouldn't restrict it to a spatial error model, an SLX model, then we certainly shouldn't restrict it back to OLS. But we can do that test anyway. And you see the extremely low p-value. And here we're restricting, degrees of freedom is 7. So we're restricting all 6 of those spatially lagged x coefficients to be 0 plus the error multiplier to be equal to 0. So 7 degrees of freedom. So this is saying probably not the best idea to just use OLS here. So this is where I would stop, and I would just say Spatial Durbin Error model is right. Now we could similarly go through the same kind of process if we were convinced that we needed a global model. So we'd start with a Spatial Durbin model that has the lag y's and the lagged x's, and then we could do 4 different likelihood ratio tests to see if an SLX is more appropriate, the SARAR is more appropriate, or the spatial error model, or the OLS would be more appropriate. Now here is a problem though. What if you had no idea? What if you just racked your brain and you could not decide whether you had a local or a global process? Well, there's not a lot of great ways to test that. Now, there are some Bayesian methods. You could compare the Spatial Durbin model to a Spatial Durbin Error model using some Bayesian methods, and it would tell you which model is more probable to be correct. And if you want, I can bring somebody on later and have them talk about how to do that. That is probably where we'd get into using MATLAB instead of R, because I'm not sure how to do that in R. I'm a frequentist, not really a Bayesian. Similarly, there are a lot of ways you can specify these weights matrices. There's not a frequentist approach to compare different weights matrices because those models with different weights matrices are not nested. Just like the Durbin model and the Durbin error model are not nested, you can't use something like a likelihood ratio test to see which of those two is more appropriate. So when it comes right down to it, model selection can be tough, and you can use things like root mean squared error or AIC, BIC, Mallow's CP, all these different flavors of goodness of fit measures with penalties for overspecification. But at the end of the day, let those measures inform your choice of the right model. Don't let those measures make the decision for you. It's really important that you try to make the decision as best you can, at least in my opinion. Let me show you a couple other things we can check. So one thing you'll probably want to check is, do you have heteroskedasticity in your model? So we decided we were going with this Spatial Durbin Error model as our final model, but we want to make sure we don't have heteroskedasticity. Or if we do have heteroskedasticity, how big of a problem could it be? So here's our studentized spatial Bruce-Pagan test, and it's telling our p-value is 0.07. So maybe we could get away with saying that we don't have heteroskedasticity here. What should you do if you do have heteroskedasticity? The advice I have been given by the experts is generally to say, well, look, heteroskedasticity is going to affect your p-values. It's not going to bias your coefficients. It's just going to affect your standard errors and your p-values. And it's probably, heteroskedasticity is probably not going to cause your p-values to be that far off. So again, this is probably. So if you have p-values that you're interested in, and those p-values are, say, 0.0001, heteroskedasticity is not likely to cause that p-value that you're looking at, 0.0001, to be that far off to where you should be concerned. Now, if you have a p-value that's 0.04999, and your alpha you want to use is 0.05, maybe you should be worried if you have heteroskedasticity that that p-value could be a little higher or a little lower, but could be a little higher, all right? So this is our way to check for heteroskedasticity with spatial models. Another thing you could do if you wanted to use goodness of fit as a way to kind of feel out how well you feel about this model you just estimated, then you can do like a pseudo R-squared, which again, it's not a true R-squared because we're not using OLS, but it is looking at the ratio of the total sum of squares on the bottom and the 1 minus the sum of squared residuals on the top. So it gives you kind of an idea of what percentage of the variation the spatial model is predicting. And so here we're getting an R-squared for this Spatial Durbin Error model of about 22.6% of the variation in the y variable being accounted for, being explained by this model. Not too bad for most social science kinds of models. Actually, not bad at all. So I hope you've enjoyed this series. I hope you find my mother of all our spatial econometrics handouts to be useful. I have all the commands we've used here. I have information on the likelihood ratio tests here. I have some more information on the back about the Lesage and Pace method for specification and the likelihood ratio stat. This handout's not perfect. These videos have not been perfect, but I have hoped to give you access to some of this information, and I hope that you have learned a lot. I've certainly learned a lot by making these videos. So if you want to learn more about spatial econometrics and you want me to make more videos, please let me know. Please support me in any way you can. Share my videos with friends and colleagues. Feel free to subscribe to my videos. If you really love me, support me on Patreon. But I really do appreciate all your letters of support and all of your comments that you've made on my videos. And again, if you want more of this, let me know. If you don't, fine, I can move on and make some videos on other subjects. So this is Dr. Berkey signing out and wishing you the best of luck in all of your research and all of your learning about economics and econometrics. This has been a lot of fun. It gives me a lot of pride to work with you guys. And as always, I wish you the best of luck in your economic studies. Bye-bye.